Now we come to the final Stata example. For this example, we are going to learn how can we detect the problems of multiple linear regression using Stata. First and foremost, we rerun the regression, the multiple linear regression of this MPG model. So we get the result as we seen earlier. So we are going to begin with the omitted variable bias test. So the command is start ov test. This is the omitted variable test, and press enter. We are going to see the result of Ramsey reset test for omitted variables. The null hypothesis is model has no omitted variable. So we want the p-value here to be insignificant or greater than 0.05 so that we cannot reject the null hypothesis. What we get here is as what we need, which is insignificance of V test. Therefore, we don't have any issue of omitted variable bias. Next, we are going to run multicollinearity test. The command is as simple as VIF. Variance inflation factor. Remember, we want VIF to be less than 5 so that the IVs in the model are not perfectly or are not highly correlated to each other. So we can see here the VIF value is very small, 1.54. So it means that we get no issue of multicollinearity whatsoever between the IVs. Then we come to the heteroscedasticity test. We have learned Bruch-Pagan test and White test. So let's do for Bruch-Pagan test first. So the command is start head test, start HET-TEST head test, and we can see here this is Bruch-Pagan, or also known as Cook-Wisberg test for heteroscedasticity. And the null hypothesis is constant variance. We want the p-value to be bigger than 0.05 so that we cannot reject the null hypothesis of constant variance. Apparently, the result here is significant. It shows we have the issue of heteroscedasticity in the regression of MPG against weight and foreign. So we need to control for heteroscedasticity. So that is the Bruch-Pagan test. We also learn the White test, so we can run White test start im test, start im test, and then comma white. So this is to do White test for heteroscedasticity, and we can see here the null hypothesis is homoscedasticity and the alternative hypothesis is heteroscedasticity, and we have the p-value here which is lower than 0.05, again showing that we have heteroscedasticity problem. Now we come to the autocorrelation test. For autocorrelation, we understood that it must be done on a time series data. Since this data is not a time series, this is cross-sectional data, so let's assume that this data is time series, and we have to create time identifier for this data. Just for the purpose of learning process, we assume that. So how to create a time identifier? The command is gen time, whatever name we want to give, and then underscore n. So we tell Stata to create time identifier. So underscore n mean it start from 1, 2, 3, 4 until the last observation as the last period. So click enter. So we can see that time is now present among our variables, and we can see time is denoted as number 1, 2, 3, 4, sort of indicating the time periods that we have here, 74. This is only meant for testing for the autocorrelation. It is not practical to assume that one car after another is similar to the time periods. So just for the purpose of testing for Durbin-Watson and Bruce-Godfrey, we assume this is time series data. And then we need to tell Stata the time identifier. So TS as set means we want to tell Stata, take this data as time series data. What is the time identifier or time period identifier? So the name is time. So now we have sort of time period 1 until 74. And we need to do the multiple linear regression of MPG, weight, foreign for this quote-unquote time series data first. Then we can test for the Durbin-Watson. Remember, Durbin-Watson test, you must get the Durbin-Watson statistic closer to 2 so that we don't have any serial correlation or autocorrelation problem. Remember, we have to find the D upper and D lower value first from the Durbin-Watson statistic. We have N74 and the number of IVs, number of K2. So the Durbin-Watson statistics will give you DL and DU according to the number of K2 here is K equal to 2, and N74 or 75 here 1.57 is DL, 1.68 is DU. So we are going to put the 1.57 here, 1.68 here, 2 is in the middle. 4 minus du, we are going to get 2.32 and 2.43 here. So we are going to test for Durbin-Watson statistic using this command, and let's see what will be the value of the Durbin-Watson statistic. So we get 2.42 here. So 2.42 seems like we are in zone of indecision. Remember, this is 2.32, this is 2.43, so the result is 2.42, sort of like we are in this zone of indecision. So using Durbin-Watson, we cannot confirm the presence of serial correlation. So we need to use Bruce-Godfrey, where we learned earlier, can also test for first order autocorrelation. So let's move to first order autocorrelation test using Bruce-Godfrey. The command is start begot F-R-E-Y. We can see here Bruce-Godfrey LM test for autocorrelation, number of lag is 1. Here we have p-value greater than 0.05. It is not significant. So we cannot reject this H null of no serial correlation. Therefore, we don't have the problem. And we can also test for higher order lags of serial correlation using Bruce-Godfrey test. So how do we do that in Stata? We can add this command lags after start B-Godfrey. So how many lags? We can put in bracket here 1/10. Let's say we want to test for up to 10 order serial correlation for this model MPG as a function of weight and foreign. So we can add this additional option here and press enter. So we can see Bruce-Godfrey LM test for autocorrelation for this leg 1, leg 2, leg 3 and so on. So we can see that all of the p-value are not significant, indicating that regardless of the lags or the order of serial correlation, we don't have problem of serial correlation in this MPG model. Thank you.